Doppler shift. So I've sketched out the situation here. There's a police car behind you that's stationary, it's not moving. There's a police car in front of you, it's actually moving faster than you are, it's going at 30 meters per second. And you're sandwiched in between, moving at 20 meters per second. And the two police cars emit the exact same frequency, their sirens do. And if everybody was stationary, you wouldn't hear a beat frequency. You'd hear the exact same frequency from each of the police cars. But because there's motion involved, the frequencies are going to be shifted a little bit due to the Doppler effect. And they're going to be slightly different, and we're going to hear a beat frequency. Okay, so let's take a look at the frequency. Well, we're going to treat each police car separately. First, we're going to look at the frequency observed from the police car that's stationary, and then we'll do the other one. I'll call the stationary police car A and the other one B. So here's the equation for Doppler shift, for Doppler effect. And your textbook may be slightly different on the subscripts, but basically it's the same equation that you're going to see in every textbook. This is the observed. That's the frequency observed by the listener, and it's shifted from the actual frequency at the source. That's this one. So F sub s here, that's the actual frequency being emitted by the source, and it gets shifted a little bit due to the motion. And the V here with no subscript, that's the speed of sound. And then we've got the speed of the listener. And the speed of the source. And then there's a whole table of, you could try to memorize it, of whether the signs are positive and negative, when they're positive, when they're negative, when the listener is moving toward the source or away from the source. But I like to just think about things for a minute and make sure I get my signs right, make sure they're shifting things in the right direction. So let's take a quick look at what happens from car A. Frequency from car A. So I'm going to call that frequency sub A, and this is the frequency at the listener due to car A. The speed of sound is given in the problem as 344 meters per second. The listener is moving now. That's you. You're moving at 20 meters per second. But let's think about this for a second. If we add 20 meters per second to our numerator, what's going to happen to the frequency? It's going to make the frequency larger. And the frequency doesn't get larger when you move away from the source. The frequency should get smaller. So this needs to be a negative 20 meters per second. We need to make the numerator smaller in order to make the frequency go down. Your motion away from the source will make it sound like a lower frequency. And then let's think about the source. Now the source is not moving, so in this case it's easy. We just put a 0 in there. But again, think about it the same way. If the source is moving toward you, then the frequency would have to go up. So you would want to make your denominator smaller. You'd put a negative number there. And if it's moving away from you, the frequency would have to go down. You'd want your denominator to be bigger. You'd put a positive number there. So just think about it a little bit. Make sure it shifts you in the right direction. All right, and our siren is actually 1,000 hertz. So we're going to multiply this out. I got 0.9419 times 1,000. Which is 942 hertz. And it's got to be a little bit lower, right? The police car is stationary, we're moving away from it, and so the frequency has to be a little bit lower. This frequency we hear is going to be shifted lower, and it is. So good, that makes sense. If you'd like, you could stop the video now and see if you can do car B all by yourself, and I will do it here also. Speed of sound, 344. Now, you're moving, but you're moving toward the source. So that would make the frequency higher. We need to make the numerator larger. So we're going to add 20 meters per second to the numerator. In the first part of the problem, we subtracted because you were moving away from the source. In this case, you're moving toward the source, so that makes the frequency shift up a little bit. And in the denominator, now we put the speed of the source. And the source is moving away from you, which makes the frequency shift lower. So we need to increase the denominator by putting a positive 30 in the denominator. That shifts it in the right direction. And this is all multiplied by 1,000 hertz. And what do I get? 0.973 multiplied by 1,000 is 973 hertz. And a beat frequency occurs when you have two frequencies that are very close together. That's how a musician tunes their instrument. They hold up a tuning fork, which gives them the exact frequency they want, and then they pluck the string on their guitar, and if they're slightly different, you hear these beats, and they tune the frequency of the guitar string until those beats go away. So beats, very helpful when you're tuning instruments, and that's just the frequency of one minus the frequency of the other. And what do we get? Plug in the numbers, 973 and 942. .31 hertz. I'm not going to worry about the fact that which one's higher or lower. I just care about the magnitude here, the absolute value. So we get a beat frequency of 31 hertz due to the fact that both of these frequencies are shifted. When the first police car, the stationary one, that gets shifted down, right? That's a lower frequency. And then the other two, you're moving toward the police car, but the police car is moving away from you faster than you're moving toward it. So that's also a shift down to a lower frequency. And both of those frequencies are different, so they give us beats.